So section 9.2 looks at significance tests specifically around a population proportion. This particular video is going to cover just the first three, and then the one after that we'll talk about the power of a test. So we go back to our basketball player, and they claimed to be an 80% free throw shooter. Took a sample, and he made 32 out of the 50 throws, which is a 64% free throw percentage for those 50. The question is, does it provide convincing evidence against his claim? And so what we're going to do is we're going to perform a significance test. And the significance test always assumes the null is true, and everything we do in the calculations up to the point of calculating the p-value uses the population proportion or the null proportion as the building block. What we did in the first part of the chapter is we simulated those 50 shots lots and lots and lots and lots and lots of times. And this was the distribution that we got when we simulated that lots and lots and lots and lots of times, assuming that it was an 80% shooter. So we got a sample distribution as an 80% shooter. And when we do that, then we look at the p-hat, then we look at the proportion that occurred in the sample, which was 64%. And then we look where in the distribution does it 60% land, and we look at it and to the extreme of it to calculate the p-value. In this case, the p-value was 3 out of 400, which is 0.075. And we use the simulation and the sample distribution for the simulation to calculate our p-value, and then we can make a conclusion. Since the p-value of 0.075 is less than the alpha of 0.05, we reject the null hypothesis. We have convincing evidence that the shooter has a free throw percentage that is less than 80%. This was using simulations to create this sample distribution, but we can use, assuming that our conditions are met, we can use what we know about normal curves to do that. So in Chapter 8, we introduced 3 conditions that have to be met before we can construct a confidence interval. These same 3 conditions need to be met. So we know what the conditions are: random, 10%, large counts. But remember, the random, if we don't have evidence of a random sample, we throw out the whole thing, we can't do anything. 10%, if it doesn't work, that relates to the ability to use the standard deviation formula. I need a new stylus. Oof. And the large counts allows us to use normal calculations. And we're always using for all of the work we're doing until we have that distribution built, we're always using the p from the population. Okay, so since we have checked, or we didn't, but we would check to see that the large counts condition is met, that means that the sampling distribution is approximately normal. It does in this case. We had more than 10 successes and more than 10 failures. So we can go ahead and build a distribution based on that 80%. And my stylus just broke, so we're going to see how I do with just using my finger. Here we have our 80% in the center of our normal, and then we go ahead and calculate the standard deviation, which we can do because the 10% condition has been met. And then so our standard deviation is added. Here's our 1 standard deviation, 2 standard deviations, 3 standard deviations, etc. And our test estate, the thing we're looking for to see how rare it happened just by chance is here our p-hat. I'm going to blow it up a little bit. So here's our normal curve. Here is the thing that happened when we took a single sample. And it's right here. And so we're looking for the area of that tail. That looks dumb. Let's do that again. We're looking at the area under the tail. I can't do it with my finger. Sorry, guys. So this doesn't look any different in the long run to the work that we've done with normal curves before. So we basically found a value, and we're going to find the z-score for that, and then we're going to find the area to the left of that, which we've been doing consistently. So the test statistic tells you how far you are from the null parameter value, which is the center of that normal curve, and it's standardized. So it allows us to use those same things we've been doing, the z-score, how many standard deviations away from the mean type of thing. And so in this case, our z-score, our test statistic, is called, it takes the statistic, in this case, the 0.64 that came from the one sample, and I don't have a stylus, so if this comes out goofy, that's supposed to be subtraction there. Whoop. So 0.64 minus the parameter, which is 0.8, and then when we calculated the standard deviation, that was 0.0566. So we're going to go ahead and get a negative standard deviation, a negative z-score is negative 2.83. So we're way, way, way toward the third standard deviation away. And remember, third standard deviation away is 99.7. So we should expect this to be a really small number. So the reason that we can use a normal curve, when the conditions are met in a situation that it's random, 10%, that means we can use our standard deviation formula. Large counts, that means our sampling distribution is approximately normal. Then we can go ahead and build that curve based on those assumptions that are correct, and then we can go ahead and compare that, that sample statistic to what would happen by chance. And we can use the standard normal distribution to help us to figure out our p-value. So the z-statistic tells you where it lands on that normal curve, and then the p-value tells you the proportion to the extreme of that. So we've found the z-score of our 0.64 and to allow us to use our normal calculations to find the area under that curve. And that area under that curve, that little tiny bit to the left, is just how frequently it would happen by chance that you would get a 0.64. Remember, we're going to be comparing that probability to our alpha level to decide if there's convincing evidence that they really aren't as good as they say they are. So the negative 2.83, if we use our table and find the probability of that area, or that area under the curve, to the less than negative 2.83 is just, it's really small. It's a small number. Excuse me, please. It's less than 1%. So since if the null hypothesis is true and the player makes 80% of his free throws in the long run, there's only about a 2 in 1,000 chance that the player would make as few as 32 out of 50 shots. That low number allows us to make a clear statement of rejecting the null. So we would say, since our p-value of 0.0023 is less than the alpha of 0.05, we reject the null. We have convincing evidence that the player has less than an 80% free throw percentage. So this is what the book says. I'm just going to read it. But basically, a significance test uses sample data to measure the strength of the evidence against the null hypothesis. But the test compares a statistic, but everything you've calculated ahead of that uses the value of the parameter. You use the value of the parameter as your null, use the value of the parameter as the center of your normal curve, use the value of the parameter in the test statistic. The only time you use the statistic itself is when you are calculating the test statistic or labeling your curve where you're going to be looking to the extreme of. We're going to want to make sure that we follow our 4-step plan. We're doing it in class. I don't need to read these things to you, but you remember that the state includes the hypotheses. Not remember, I said it incorrectly in class. You want to state your hypotheses at that point, and at what significance level, and any parameters. Notice there's no mention in the state about the data that's been collected in the one sample. You're going to choose the appropriate inference method. Sometimes you're going to use a one sample z-test. Sometimes you might choose to do something else, including making confidence intervals, and we'll talk more about when you would want to do the other. If you are choosing a one sample z-test, then you're going to go ahead and perform the calculations of calculating that test statistic, finding the p-value, making the conclusion, using that template that we have considered. So I mentioned earlier, and I'm going to try and write these subtraction signs that didn't come through, that you're going to use the population parameter to do your calculations of creation of the curve and the standard deviation and all that stuff. You'll notice in this particular it is shown as p sub null, because they're telling you that you're using the proportion from the null hypothesis in your thing. Most of the time you're going to be calculating a one-sided test, and here you have what it would look like if you were calculating a test where the proportion was going to be greater than the null, and you're going to be looking at the extreme that way, so you're going to do a 1 minus when you get your probability, unless you're using the calculator. And then if it's less than, you're going to go ahead and take that z, and it'll, when you use your table or the calculator, it'll automatically give you the proportion that way. And then if your hypothesis says that they're different from one another, you're going to look at the proportion that both it's less than and greater than the z value that you calculate. So I wrote on this before I spoke on it, so I'm going to have to write it again. So the p-value in a one-sided tail looks at the area of one tail of the standard normal curve, the tail that's specified by your alternative hypothesis. In a two-sided test, remember, it's just the idea that it is different from the null, not indicating whether it's greater than less than, just different. Because of that, we have to pay attention to both the tail on one side, and you'd also have to find the tail on the other side. Because they're symmetrical and equal, you can simply find the tail under one, the area under one tail, and double it if it is a, anytime you have does not equal. So unless we're going to be doing a bunch of simulations, if we meet all the requirements of random 10% on large counts, we can use our normal curve to build one based on the population proportion and the standard deviation of that population proportion. Then we can use our z-scores and our table or our calculator to find the area under those tails, and we have information to make a decision about whether the sample is enough convincing evidence to reject or to fail to reject the null.